Here we are. Now we're recording. Okay, so what you want me to mention some of the things? Well, my family has been ill. I think I mentioned that in the email. Everybody in the family got a stomach bug, and so it's been a busy weekend just looking after the kids and looking after my wife. And then I was sick, and they were looking after me, and that kind of thing. I didn't get it as bad as they did, thankfully. But I don't know, whatever. I lucked out. But now that I'm back, I'm even more behind. And so I forgot to check on what was happening, but now I know. We're reviewing for Quiz D. So Quiz D, we haven't learned very much about sequences and series yet. We're still very near the beginning of our study, so let's review some things. Sequences and convergence of sequences. This is one of the first things we study, just what is a sequence and what does it mean for a sequence to converge. We reviewed limits and limit tools, right? And techniques. Things like L'Hopital's rule and such. Squeeze theorem is one that came up. Well, actually, we didn't do the squeeze theorem last week, but the squeeze theorem can be applied for one of the sequences in the exercise set that I gave you guys that I haven't finished grading yet. We might want to review that today. We've got sequences and the convergence of sequences. This is the one of the foundational ideas, an infinite sequence and what it means for it to converge or diverge. Then we have series and the sequence of partial sums. And the sequence of partial sums defines the convergence or divergence of the series. Now, we studied that directly. We spent a whole day in class practicing working with series and partial sums and trying to figure out convergence based on looking at that. Then we learned a couple of other things. We learned two special rules. We learned recently the divergence test, the nice, quick test we can review today, and the integral test. Okay, we can review both of those. Okay. These are the things that will be covered on the quiz. So let's start with sequence convergence. Here's an example from the exercise set. What about the sequence an equals -1 to the power n over n squared, or something like that? That was very similar to one of the examples on the exercise set. So this is equal to like -1 over 1, and then 1 over 4, and then -1 over 9, and then 1 over 16, and so on. -1 over 25, 1 over 36, etc. That is what that sequence looks like. Now, converges or diverges? Converges. Probably converges to, what do we think it converges to? the sequence, not the series, but the sequence, probably converges to 0. Yes. Good. Now, how do we actually show that? Well, can you just do the limit as n approaches infinity of -1 to the n over n squared? What would that even be? I mean, what is the limit of the numerator, for example? It doesn't exist, right? Because it's oscillating between 1 and -1. So yes, the squeeze theorem is what we can use here. We can say, well, whatever -1 to the n over n squared is doing, it definitely lies between -1 over n squared and +1 over n squared. I mean, between is not necessarily the right word to use. It's either equal to -1 over n squared, or it is equal to +1 over n squared. It never ends up being genuinely between them. But if you write the inequality with less than or equal to, then it is a valid inequality, right? Like, this is true. It's either equal to this or it's equal to that, right? But this remains true. So yeah, you can use squeeze on this, and this approaches 0 and this approaches 0. So this guy approaches 0 by the squeeze theorem. Yep. So that was what we didn't talk about the squeeze theorem last week. We didn't review that, but that is a useful tool for these sorts of alternating sequences, right? Especially. Okay. So that's a good place to get started. Most of the time, when you're determining convergence of a sequence, it's fairly straightforward. It's just take the limit of the sequence, however the sequence is defined, and determine what that is. We might want to spend a little more time on this one, looking at partial sums and studying a series from that perspective. Does that sound good? Let's look at one of those. Unless is there anything else that you would think is on this topic, the first topic, that you want to study or that you want to go over? I will open the floor to that for a moment. Before we move on. Okay, so let's look at an example. Let's explore number 75 from section 5.2. We'll look at this example. This is a series. Actually, that's not quite what I wanted to look at. Sorry, that's not what I meant. Let's hang on a second. That's kind of working backwards. Hang on a second. That's not what I want to do. Yikes. Here. Not actually what I wanted. What I want to do is look at it from the other direction. I'm gonna flip it around. Yeah, let's say we have a sequence, which is 1 over n minus 1 minus 1 over n. Or equivalently, 1 over n times n minus 1, I believe. N minus 1, is that right? I think that's right. Yeah, 1 over n times n minus 1. Did we do this one last time? I think we might have. Or no, we did n times n plus 1. It's very similar. Let's examine the series summing from 1 to infinity, 1 over n times n minus 1. So this is going to be like, actually, we can't go from 1 to infinity. We better start at 2. Because if we start at 1, we're going to have a problem, because this is 1, that would be 1 minus 1, which is 0. That's not gonna do. So we better start at 2 this time. So we'll do 1 over 2 times 1 plus 1 over 3 times 2 plus 1 over 4 times 3 plus etc. So what we have is like a half plus a sixth plus a 12th and so on. I'm just plugging in the numbers 1, 2, 3, or rather, sorry, starting at 2, and then 3, and then 4, and then so on, to the sequence definition, this sequence, and obtaining those terms, which are then going to be added together, right? So partial sums. We're going to start with S2 for this because n starts at 2. Okay, so S2 would be 1/2. S3 is a half plus a sixth. It's going to be S2 plus S3. Sorry, A2 plus A3 is the added together, right? And then S4 is a half plus a sixth plus a 12th, and so on. S5 would then be a half plus a sixth plus a 12th plus, what's the next one? 1/20th, I think. It'd be 5 times 4. So this is one of the main things I'm going to be asking you to do on this quiz tomorrow is take a sequence and get from it a new sequence of partial sums, which are like progressively get successive approximations of the full infinite series. Right? This is 1/2 is the worst possible approximation of the series because it's just like the first term in the series and that's it. It's ignoring everything else. But then the second number, a half plus a sixth, which would be what? That's like a 4/6 or 2/3. That is your next slightly better approximation of the series, right? Because it's the first 2 terms added together, and the error, which is everything you left out after the first 2 terms, is smaller. When you add 2/3 plus a 12th, we get 9/12, or 9/12, which is 3/4. And now we have a slightly better approximation, right? And we keep going. So 3/4, I think we're going to get, we should get 4/5 here. And so on. Then it's going to be 5/6. And we see the pattern, right? This is, like I said, very similar to the one we worked on in class the other day. This is the sort of thing I'm going to be asking you to do, right? Take a series with its defined sequence, right, that you're adding up, and then make a new sequence. We'll switch colors here. A new sequence for the partial sums. And then from that, you can figure out a formula for SK. And we look and see that the S2, it was a 2. If 3, it's a 3. 4, it's a 4. We're seeing here that whatever is in the denominator is matching the subscript on the partial sum. So this is going to be k minus 1 over k, like that. And that's our, we went from an to sk. All right. And this allows us to figure out what the series is converging to, and if it converges, right? So now we can take the limit as k goes to infinity of our sk formula and get whatever that is, right? This is what the series converges. So the series converges to 1. And you can literally write that this infinite sum of numbers equals 1, right? If you could add up all infinitely many terms in that sequence, that infinite sequence, it would equal 1. Okay, and so since this is math and it's all sort of like theoretical, it's all just sort of an abstract idea on paper, we can literally add up that infinite sequence, all infinitely many of them, and say that equals 1. Okay. So that's the second of the 2 bullet points over on the left there. Questions, or would you like me to, would you like to look at maybe one more example of that? Look at one more example. Do this. It is the 28th. I've got some catching up to do with something where we can't so easily see the pattern. Sure. Let's see. It's a little bit, so there is a space in between, like, easy to see the pattern and impossible to see the pattern. And you're asking me for something in between that. And it's like there's a lot of things over here, and there's a lot of things over here, and there are fewer things in between them. So you're asking me for something that lies in here, and there's fewer examples of that. So so let me see if I can come up with something. Yikes. Okay, we should be able to do this. I don't know if this might still be a little bit easier than what you would like, but we can try it. Let's do the sequence is 1 over 3 to the n. Oh, what did I give you on the exercise set? Forgot what that was. I might have found a really nice one for the exercise set. 1/3 to the n is, again, sort of similar to one of the ones we looked at in class the other day. On the exercise set, I gave you, oh yeah, that one is a little bit, it's a little trickier, perhaps. It is a telescoping series. That's right. The one on the exercise set is telescoping. Let's look at this one, and then we can take a look at a telescoping series. We could look at the one on the exercise set, or we could look at something similar. So 1/3 to the n is our sequence. We want to add it up. We can start from 1. So we have 1/3 plus 1/9 plus 1/27 plus 1/81, and so on. Adding up powers of 1/3. Okay. So our partial sums are going to look like this. Let's start adding these up and see if we can see a good pattern. So we have 1/3. If we add 1/3 plus 1/9, we have 4/9. We add 1/3 plus 1/9 plus 1/27. We have, let's see, 4/9 plus 1/27 is going to be, I believe, 9/27, right? So now we're going to take the 9/27 from before and add 1/81 and get oh, I think I screwed that up. This isn't 9/27. This is 4. We're tripling it, so it's 12. Is it 13/27? Four ninths. We're tripling 9 to get 27. So tripling 4 is 12 plus 1 more is 13. There we go. Yes. And then to get over 81, we're going to get 9. We've got to triple the 9 to get 27 and then add 1. So that's 29/81. Oh, I think this is actually fairly well in between, because I like this, actually, because our denominator is pretty obvious, but the numerator is not so obvious. What is SK? Well, when we have 1, we have a 3. When we have 2, we have 9. When we have 3, we have 27. When we have 4, we have 81. What's our denominator pattern? How did I screw that up? It's 9/27. We got to triple the 9. No, isn't it? We got the 13/27. Yep, we got that. Okay, so our denominator is 3 to the k. Yes, our denominator is 3 to the power k. We're looking at powers of 3, right? Like 3 to the power 1, 3 squared, 3 cubed, 3 to the 4th, right? 27. Okay, guys, is my arithmetic right on this one? Oh, that's what you're telling me. I forgot. I changed that one, but I didn't change this one. So this is, yeah, you're right. So this is 13. So we have 39 plus 1 is 40. You were right. Yep. Thanks, guys. Sorry, I was so slow on the uptake there. You make one mistake and it persists, right? You got to fix it everywhere. You've all been there. Sometimes we faculty end up in that position too. We all take it easy on each other. All right. So now we can look at our numerators. 1, 4, 13, 40. What is the pattern? How can we write the numerator as a function of k? Wow. What is the pattern? Think.
Is it 1/2 3 to the k and then a -1?
Whoa, is it? Where'd you come up with that? Half of 3 to the k and then -1. So like, well, half of 3 to the k isn't going to work very well because you're going to have a half of a multiple of 3, and that's not going to be an integer anymore. Oh, maybe it's like 3 to the k -1 and then divide by 2. Or so what Braden's saying is a half of 3 to the k and then -1/2 instead of -1. So it's like having the -1 inside in the numerator instead of outside of the numerator. Like that. Okay, guys, you got to explain how are you coming up with that pattern? Because I think that's what a lot of us are worried about, right? It's like, okay, great, I can get the sequence of partial sums, but how do I magically figure out the pattern to get to here, right? I think this is correct, by the way. I think this is correct. So this should be 3 to the k -1, and then there's going to be a 2 in the denominator. So how could we figure this out? So if we are explain this. If your denominator involves powers of something, there's a fairly good chance the numerator is going to be somehow based on those same powers. One strategy is to sort of look at the differences. So here we have a +3, and then we have a plus, what is that? 9, and then we have a plus 27. Is that right? Yep. And so if you look at the differences between the numbers, and those differences are, if there's a pattern in the differences, then we can work backwards from that to figure out the pattern in the original numbers. So we can see that the difference between these numbers are powers of 3. 3 squared, 3 cubed. So in a way, you have sort of a start at 1. How would you say that? It would be I'm not sure how to explain how to do that. But this at least suggests that it's going to have something to do with powers of 3. So then if you look at the powers of 3 and you go, okay, so you got 1, 3, 9, 27, then you can start to try to extract this, and you can see the relationships between them. I don't know. I really want to hear from you guys how you came up with this. Like, how did you figure out that the pattern here is ×2 and then +1, ×2 and then +1 equals 26 + 1 is 27. Like, how'd you get that? Oh, it's half the denominator rounded down? Oh, that's true, it is. Cool. Okay, yeah. 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 Yeah, I don't think that there isn't like this is basically a hard thing to do, this sort of pattern recognition. There are some tricks. I don't teach this like explicitly. So I don't really have like any particular suggestion for how to do it. Like most of these examples we're looking at here are like, it's just sort of like if the pattern's not immediately obvious, then maybe just try a different approach. But I'm going to try to stick to things that are fairly simple to do. So if we're not in this area over here, it might be not a good quiz problem. But there are also the telescoping ones, which are, I would say they're not like an obvious pattern, but they are easy to handle because of the way things like cancel out. So maybe we can look at a telescoping example as well. So usually telescoping happens when you have like an n, something involving some function of n or n plus 1 minus a function of n, something like that, where you have consecutive values n plus 1 or like n minus 1 and n, consecutive values like that, and there's subtraction. Because if you sum this up, something of this format, you get stuff like f of 2 minus f of 1. Or sorry, it should be the other way around. I just realized I did this backwards. Sorry. It's usually the other way around. Doesn't have to be. But it's usually this way. So it's more like f of 1 minus f of 2. And then you add f of 2 minus f of 3. And then you add f of 3 minus f of 4. And so you basically get these canceling down. And it's going to cancel all the way down. So you're going to get like f of 1. In the end, you're going to get, I'll put an arrow. It's going to approach f of 1 minus whatever the limit as n approaches infinity, f of n is going to be. So whatever that limit is, that's what you get is subtraction. So for example, let's say you're summing up cosine of n minus cosine of n plus 1. Something like that. So what you get is cosine of 1 minus cosine of 2 plus cosine of 2 minus cosine of 3. And then plus cosine of 3 minus cosine of 4, etc., right? So these cancellations happen like that as you go. If we are a little more cautious about setting this up, we can look at the partial sums. Cosine of 1 minus cosine of 2. S2 is going to be cosine of 1 minus cosine of 3. S3 is going to be cosine of 1 minus cosine of 4 because of the canceling, and so on. So what we get is the pattern SK is cosine of 1 minus cosine of k plus 1. So because this number is always one more than that number. And so then we just have to ask, well, this is going to sum up to cosine of 1 minus whatever the cosine of k is approaching. So limit as k goes to infinity, cosine of k plus 1, right? So whatever that is approaching, that's what we're subtracting, right? So we're taking this is the limit of the partial sum. Okay, gets this. Now, this limit oscillates and does not exist. So when you do cosine of 1 minus an oscillating thing, it's like you're subtracting a wave or something that's it's dots, but it's in the sort of pattern of a wave, right? It's like a cosine wave. You're subtracting that from some finite value, it's still going to be a wave. It's going to be like shifted and flipped upside down or whatever. So this is divergent. Okay, that limit doesn't exist, so it's going to be a divergent series. Okay. Oh, I just realized we never finished this one. We forgot to finish this one. So we moved on. I moved on to the telescoping one, but that was a little bit preemptive. I should have finished this one first because we never finished 1/3 to the n, summing up 1/3 to the n. We got our expression, our like formula for SK, but we didn't take a limit of it. So what is the limit as k goes to infinity of 3 to the k minus 1 over 2 times 3 to the k? What is this going to be? Yeah, it's going to be a half. We could do a little bit of algebra there if you're not sure. Okay, let's do a little bit of algebra. Let's distribute the division over the subtraction in the numerator. Both of these are divided by 2 times 3 to the k. 2 times 3 to the k. If we distribute that, then you can see the 3 to the k cancels out here, and this is just 1/2. So there's the if it cancels, we have 1/2. So that first term there is 1/2. Then this term, 1 divided by 2 times 3 to the k, as k goes to infinity, 3 to the k is going to approach infinity, and we have 1 divided by bigger and bigger numbers. So that is going to approach 0. And so yes, so we just get 1/2 from the first term minus 0 from the second term. So we have 1/2. So that's what we can say. This series sums up to 1/2. It converges to 1/2. Okay. We're a bit short on space, so I'm going to export that. There we go. Let's review a couple other things. Let's review the divergence test. Okay. If you are looking at this, and the question is, does this converge or diverge? We can apply the divergence test. And remember, the divergence test is a quick test for divergence. And it just says, just take the limit of the sequence. You don't need to make the partial sums. Start by just looking at the sequence and look at its limit as n goes to infinity. This sequence, 1 minus 1/n, 1/n is going to approach 0, of course, so this is equal to 1. And if that is anything other than 0, which it is in this case, the series diverges. If it's anything other than 0, okay? So the divergence test applied to that series tells us that it diverges. The divergence test can only conclude that a series diverges. Okay, so it's right in the name, folks. It's called the divergence test because that's all it can do. It can only conclude divergence. Right, so it's saying if this limit of the sequence is anything other than 0, it diverges. Now, if it's not, right, if you have something like sine of 1 over n or whatever, then like apply the divergence test to that, and take the limit as n goes to infinity of sine of 1 over n. Well, this is going to end up being sine of 0, which is 0. If it equals 0, then there is no conclusion from that test about whether the series is going to converge or diverge. It might converge. It's at least possible. It's sort of on the table still, right, as a possible outcome. But this test alone isn't going to tell us whether it converges. It cannot conclude convergence. It can only conclude divergence. That's why we call it the divergence test. Okay. So that is one possible test that we can apply. It is a nice, quick one, a good one to start with. If you, a lot of times, as we go, especially as we go throughout this unit, we'll be looking at more and more complicated series, and we'll want to apply different tests. And yes, we're going to do the integral test next. And sometimes you're gonna try several different tests on it until you find one that gives you like the conclusion you're looking for. And the divergence test is a good one to start with. Now, the integral test says that if you look at the, let's apply this to like 1 over n and 1 over n squared. If you want to look at the series, if you view that as being like described by a function, like the sort of associated function here is f of x equals 1 over x. And what we want to do is take the integral from whatever the first value is. So here we're going 1. The first term in the sequence is going to equal to 1. So we can go from 1 to infinity. It doesn't matter that much what this number is. You can fudge it if you need to. Doesn't matter that much, because the point is that it's the behavior, it's the end behavior, whatever happens near infinity, which is going to determine whether this converges or diverges. It's like the rate of decrease. So we would want to look at, and this is not meant to be an equal sign. This is sort of a connection, like a double arrow. Maybe it's if and only if. It's like the way I described it the other day was their fates are intertwined. So we want to evaluate these two integrals and see what we get. We want to see if the integral converges or diverges. So here, what we'll do is a limit as t goes to infinity, and we're going to integrate from 1 to t, the 1 over x function. Now, the antiderivative of 1 over x is the natural log of x. So we're going to get natural log of t minus natural log of 1, like that. And what is that? Natural log of t minus natural log of 1 as t goes to infinity. What is the limit at infinity of the natural log function? You guys remember that? Oh, that's just 0. Natural log of 1 is just 0. So that, yeah, so it just comes down to this. What's that? That's infinity. So that diverges. So Going back to the series also diverges. Okay. Now it's important. Okay, so yeah, that's there's a point I want to make, but I'll make that point on the second one here. So this is a way to prove that the harmonic series, harmonic series, that diverges. We proved it already. We proved it the other day. I proved it that day in class when we first looked at it. But here's another proof using the integral test. Now let's try it with this 1 over x squared. If I integrate this guy, I'm going to integrate from 1 to t, 1 over x squared. I get, let's see, this is x to the negative 2, right? So my antiderivative here is negative x to the negative 1 from 1 to t. So it looks like we have the limit of negative 1 over t plus 1. Like that, right? This is the limit of what, this is like 1 minus the limit of 1 over t. And since that's 0, it's 1. So it converges. Okay, that converges. That means that the series also converges. Okay, because like I said, their fates are intertwined. They either, the series and the associated indefinite, or is it indefinite? No, it's improper integral. They either both converge or they both diverge. But if they both converge, that doesn't mean they both converge to the same value. So the series 1 over n squared actually converges to something totally different. If I take a look at that, 1 over n squared from 1 to infinity here, here's what Wolfram Alpha says about it. Oops, sorry. It does converge. It adds up to pi squared over 6. And that is a proof I'm not going to show you, at least not today. Okay, so just because they don't converge doesn't mean they converge to the same number. The area under the curve might be equal to 1, but that doesn't mean that the sum of the areas of the rectangles also equals 1. The sum of the areas of the rectangles equals something else, but at least they both converge. That's the best you can say. Okay. Yep. So that's it. We reviewed everything. Pretty much all these topics, including up to and including the integral test, will be on tomorrow's quiz. So I hope that that's pretty okay. See you tomorrow, folks. I'd love to go over, I don't off the top of my head know like how to prove the pi squared over 6 result. But if I can figure it out, and if it's not too hard, I will try to show it to you sometime.